Today we'll just be talking about Bernoulli trials and the binomial distribution. If we flip a fair coin and define a random variable x such that x takes on 1 if the coin lands on heads and x takes on 0 if the coin lands on tails, we have the following probability mass function where the probability of x equaling 1 is 1/2 and the probability of x equaling 0 is 1/2. Right, so that example right there was just a Bernoulli trial. Or to be more precise, right, you could say that x was a Bernoulli random variable. So more generally, for any experiment with only two possible values of x, right, we say x follows Bernoulli with parameter p, our success parameter, if it has the following PMF, right, where p of x equals 1 is p and p of x equals 0 is 1 minus p, right? Where again, p is our probability of success and 1 minus p is our probability of failure. So if we dive a bit deeper here, remember this is just our PMF from our Bernoulli in the last slide. So you can just think about, yes or no coin flip style trial. Intuitively, some of these next results just make some sense, right? Our expectation is just p because, of course, the probability of failure gets multiplied by 0 and doesn't contribute to the sum. We see a very similar thing here happen during our second moment. And since 1 squared is 1, obviously it's still p. Now, from our nice definition of variance, we can use our first and second moment here, and we just simplify that, take out a p, and we're done there. Now, our MGF's a bit weirder, but really if you plug in 0 and 1 here, you see that this guy equals 1, and then since we have 1 times t, right, here we got 0 times t. So this guy equals 1, and then, we're done. Now, what if we flip the coin multiple times, right? Let's say n times. How do we model the number of times we get heads, right? That's where our binomial distribution comes into play. Now that we've gotten some of the prerequisites out of the way, we can get started here. So if we have n identical independent Bernoulli trials, right, and we let x equal the sum of all of those guys, so x sub 1 through to x sub n, then we know x equals k if and only if there were k successes in those n trials, right? And that's just because each trial is equals 1 upon success and 0 otherwise, right? So it doesn't matter how many zeros you add, it's still going to equal, the number of ones we had in that, so the k successes we had. Now, from counting, we know that there are n choose k ways, this guy right here, to have k successes in n trials. And also, since each of them is independent, the probability of getting k successes, right, we can just use our multiplication stuff from basic probability, and we see b to the power of k times our failure, 1 minus p, that's our failure, to the power of n minus k, right? Where we're just multiplying p together k times and our failure together n minus k times. So we can say a discrete random variable x follows a binomial distribution, so this guy, if it has the following PMF, the following probability mass function, where p of x equals k equals n choose k times p to the power of k times 1 minus p to the power of n minus k for k from 0 through n, right? And 0 everywhere else, where n is our number of trials and p is our probability of success. Now, before we move on here, notice that we can use this random variable in cases when we have a fixed number of trials n, where each of them is independent and each of them has an unchanging probability p. Like they can't change between, each k. So for example, you can't model the number of trials until something happens, right? As we don't have a fixed n. And you can't model, let's say, dealing cards from a deck, as your probability of success changes as you deal cards. And as such, obviously, the trials are not independent, right? So just quickly moving on here. Since our CDF is the sum over some values of the PMF, I'll let you figure that one out as an exercise. If you don't know how to do that, just make sure you review the definition of discrete CDFs in a past video. But I will show you in a moment how to find expectation, variance, and our moment generating function. So if you'd like to try those on your own, stop the video now. Remember that our binomial is just a sum of Bernoulli trials, right? And expectation, variance, and MGF all play super nice with sums of independent stuff, right? So if x is a binomial with parameters n and p, then our expectation of x is just n times p by the linearity of expectation, right? This guy here, which, you know, if you haven't seen this before, this is pretty important, but yeah, it just falls right out. And the same thing happens in variance, just because we also know the trials are independent. So our variance is n times p times 1 minus p. So you'll notice, right, these guys are all coming from our Bernoulli stuff from earlier. So the independence of trials, right, also gives us the fact that our moment generating function is just the product of each MGF. And this guy here, there's n of, we're multiplying them n times. And this is our guy from our Bernoulli trial. And yeah, we're done. Yeah, so here I've left you a couple practice problems, and give these a try. And remember, if you get stuck, you can always ask questions in the comments below. And yeah, I guess I'll see you guys next time.